Hi everyone, I'm Russell Deitrick. I'm currently a postdoc in Bern. I'll be talking today about my experiences with energy balance models from my days as a PhD student at University of Washington with the VPL group. Specifically, I will focus on EBMs applied to fast rotating planets. So what do I mean by fast rotation exactly? Well, the first point I want to make is that for planets on eccentric orbits like this shown here, the total insolation or installation varies in time, and the formulas that we're using assume that the planet does not move by much over the course of a day. So the star-planet distance can be assumed to be constant. The way that this translates into an assumption for the climate model is that all locations along a single latitude will receive the same forcing, which is, of course, not true in a spin orbit state, such as synchronous rotation. A further assumption is that the Coriolis force is strong, again, not necessarily true for synchronous rotators. And ultimately, this means that the climate is dominated by zones, and we can think of things in terms of a latitude coordinate, as I show here. The EBM that I'm discussing here is one-dimensional in latitude, although we create a pseudo second dimension by partitioning the latitudes into land and ocean boxes. The climate system is then governed by a single equation that is relatively simple, and we solve for the temperature at each latitude. And I'll break down the terms a bit here. We have the received flux, which is the insolation or installation, um, the outgoing long wave radiation, or OLR, represented by the term I there, and the heat diffusion term, which has a tunable coefficient. And there are a few additional components to our version of the model. One is an ice sheet model for the land regions, which uses Glynn's flow law and accounts for bedrock depression and rebound, and is based on this paper by Hybers and Zipperman in 2008. And a simple parameterization for sea ice that was created by Cecilia Bitz and accounts for growth and decay and some additional thermal inertia. I didn't use the sea ice model in my published work, just a simple albedo change for the ocean with temperature, but I believe this was used in a study that I'll mention later by Igor Polubsky. So what I worked on during my PhD was the climate response to extreme orbital variations for Earth-like exoplanets, what I called exo-Milankovitch cycles. Here I'm showing a case where the eccentricity varies by about 0.2 and the obliquity varies by roughly 20 degrees over tens of thousands of years. And on the left, what you see is, as a function of latitude and time, the resulting temperature and ice sheet height from the EBM. This just illustrates one way that the EBM can be useful. You can perform simulations that are hundreds of thousands or even millions of years long, which is currently not really feasible with a GCM. Additionally, we can use an EBM to map large parameter spaces. Here are a few examples. This is an exploration of what we call the eccentric habitable zone from Polubsky et al. 2020, and used the same a different version of the EBM that I discussed previously. Igor ran EBM simulations of an aquaplanet, basically no land or ice sheets, and a simple parameterization for the runaway greenhouse and water loss, which defines the inner edge of the habitable zone, and the outer edge occurs when the planet enters a full snowball state. The albedo of ice in this paper was adjusted to match the expected values for different stellar spectral types. I'm just showing the K-dwarf case here. But the colors represent the fractional habitability. So basically how much of the planet, assuming it's not in a runaway greenhouse, how much of the planet is not ice covered over an orbit. So this illustrates the dependence of habitability on eccentricity. Another interesting case is this work by Caitlin Wilhelm, who is an undergraduate at UW and is running the EBM at high obliquity to see under what conditions you might form stable equatorial ice. These planets have land and ice sheets and oceans, and like the Polubsky study, the ice albedo varies with spectral type. What the curve is showing here is the stable ice belt region as a function of installation and obliquity. The ice is stable within these curves for the three different spectral types, with snowball states below and ice-free conditions above. Another way in which EBMs can be useful is that analytical solutions can be derived to help understand things like the stability of the climate under the positive ice albedo feedback. What this plot here is showing is the predicted ice edge latitude for a low obliquity planet as a function of the forcing, which is normalized by the OLR. So we're thinking about ice caps here on low obliquity planets. On this curve, wherever the slope is positive or zero, the climate state is stable. And wherever the slope is negative, it is unstable. So considering point 1 here, a small increase in the forcing will cause the planet to warm and the ice to retreat, and the climate reaches a new stable equilibrium, which is basically within the same qualitative state. And similarly, a small decrease causes cooling and ice growth till you reach another stable equilibrium within the same state. Doing the same experiment at point 2, we see that basically any change in forcing is going to lead to a change of the climate state. This is the small ice cap instability. We see the same thing at point 3, where we have the large ice cap instability. Now, the large ice cap instability suggests that water belt states are not possible for climate. However, in GCMs, which capture many more processes that may be able to buffer the ice albedo feedback, it has been shown that water belt states can be stable down to lower latitudes than you would expect with the EBM. So this is one potential limitation of EBMs, that we sort of overestimate the importance of the ice albedo feedback. And that brings me to some caveats of this modeling approach. If we consider the EBM equation again, we've basically shoved all of our dynamics into one parameter, the coefficient of the heat diffusion term. And now, even if we allow this to vary in latitude, which gives us a little bit more sophistication, we still have to calibrate this against GCMs, potentially with many unknowns, and it's still a very crude approximation. Another commonly used relationship to take into account the effects of rotation rate is scaling the D with the inverse of the rotation rate squared, which would, the thinking is that this would enhance the heat redistribution at slow rotation rates, which is what we would expect. Some people really like this parameterization, and others I've talked to are very skeptical of it. And essentially, the argument is that the dynamics of the heat transport is just too complex to simplify in this way. I'm not sure what to make of it fully, but it's something to explore. Another comment I want to make, and this is really a word of caution, is that the ice albedo feedback fundamentally relies on the heat diffusion term. Basically, it doesn't operate if you set D equal to 0. And I pointed this out in my 2018 paper, that in the EBM used in Armstrong et al. 2014, they neglected this term entirely. And so their result, which said that orbital variations enhance habitability by suppressing ice albedo feedback, is really overly optimistic, because they really weren't capturing the ice albedo feedback. Another obvious issue for EBMs is that the radiation is very crudely represented. Here I just want to focus on the OLR, which can be simply represented by the linear relationship with temperature, as I'm showing here. There are a number of more complex parameterizations that have been used in various models, and I'm showing a comparison of some of them here. The black dotted line is just a black body curve for reference. For some of these parameterizations, which come from fits to the casting model, I've plotted dashed lines where the temperature exceeds the bounds of the fit. But an important point of this is that the OLR provides a stabilizing feedback where the stability is represented by the slope, or in linear form, just the B coefficient. And we can see where the stability fails. If we're looking at the casting model fits, we can see that at high temperatures, the the slope goes to 0, and this is the onset of the runaway greenhouse. Um, Basically, the OLR feedback shuts off, and the planet enters this unstable runaway state. Now, I attempted to use these parameterizations in our EBM, where I was exploring lots of different obliquities and eccentricities. And what would happen is that the runaway greenhouse would occur at very localized regions at specific latitudes, and that would eventually drag the entire atmosphere into the runaway greenhouse. And I don't think this is realistic, because in GCM simulations, what we see at the same sort of obliquities and eccentricities is that there's this enhanced advection that redistributes heat more effectively, and cloud formation because of convection that is decreasing the forcing. So in this sense, our EBM is really limited in both the radiation and the dynamics, because we don't capture these effects. So in conclusion, I've argued that EBMs have computational efficiency, which allows you to explore long timescale processes like ice sheets and orbital variations, and something I didn't talk about, which is carbon cycling, that is shown in several papers in the past. You can do large mapping of large parameter spaces, and the EBM is also amenable to analytic solutions. But of course, they contain a very crude representation of the radiation and dynamics, so should be used with caution. And the zonal approach really only applies to fast rotators, as I've shown here. I'll leave it to Jacob Hockmisser to talk about slow rotators. So EBMs are thus a useful tool for testing the waters, but best used in a model hierarchy. And lastly, I will just show 2 places you can find the EBM online. Thank you.